Okay, that was the middle note C, vibrating at 256 cycles per second and traveling through the air by moving molecules of air back and forth until it travels through your ear and vibrates your eardrum. And that brings us to our next topic, topic 7, waves. When we talk about waves, mainly we'll focus on two different types, sound and light. Both travel as waves. And when we talk about the mechanical forms of energy in the last topic, like potential energy and kinetic energy, we brought up that most systems run down. It's not that energy wasn't conserved, it just changed into non-mechanical forms. And those non-mechanical forms are like sound and light. Sound and light give two examples of wave behavior. And waves can be quite cool because they transfer energy from one place to another, but they don't without transferring mass. So when you have like a tsunami that comes ashore, it's the energy of the tsunami from the earthquake that happened beneath the sea that travels to the other location. So it's not the actual same water that moves, but just the energy that gets there. And when we ring a tuning fork, it vibrates air molecules, and that energy moves forth. It's not the same air molecules that travel to your eardrums that go forward. And so for the first part, we'll look at some of these characteristics of a wave. Okay, wave behavior. We'll concentrate on sound and light. They're familiar and they're interesting. There's several properties that light and sound share, but there's also some difficulties, or some differences, sorry. When you say that the word wave, people think of structures that might look something like this. Okay? Or maybe something like this. We could ask, what are the differences between these two waves? Okay, well, we could see that if we draw a midline through this wave here, and a midline through this wave here, we could see that one difference is this one goes higher up and down than that one, right? But we could see that they are, if I drew them correctly, in phase with each other. The ups are with the ups, and the downs are with the downs, like so. But that wouldn't be the case for, say, this wave. It goes higher up and higher down, and it's not in phase with the other two waves. So there's something different. For example, if we look at the point between here, this distance between there and there, we can see that that's a crest to a crest. That's a different distance from there to there. That one's shorter, isn't it? And as we already said, though, this up and down movement is less than this up and down movement there. So there's some differences of those waves. And in class, we'll do a demo with Slinky to look at that those differences. Many of you probably know what we call the up and down movement. This thing here is called the amplitude from the midpoint line to the crest, which this is called the crest here. And so the amplitude is that, and or from the midpoint line to the tip of a trough, which we call there. And this distance from crest to crest, or any point that's the same on there, so it doesn't have to be crest to crest. For example, I could go from here to there. That's called a wavelength, and you can see that that distance is about the same if I drew it properly. They would be the same. Any point on the wave to the next point on the wave is at the same point is the same distance, and that's called the wavelength. Okay. All right. Let's look at what we'll call, oopsies. This will be 7.1a. We'll call that the frequency. Well, that's what it's called. And you've heard frequency before, I'm sure. And that's how often it vibrates. So when I rung that bell, the tuning fork, at the beginning of this, it had a 256 cycles per second that it vibrates. That means each time it goes back and forth, 256 times each second. It goes up and down. Okay, so a frequency of 4 means that it goes up and down, or back and forth 4 times each second. So we write that as 4 cycles per second. Okay, the cycles though could be wave crest going by, it could be tuning fork going back and forth, it could be the pulses in light. And that is, the word cycle there is a pronoun, so it doesn't really represent any physical quantity. So the units really are 4 1/2 okay? But we have a specific name for that from someone who's worked, and it's called a hertz, abbreviated HZ. You could have 4 hertz, okay? So we'll look at some different cycle hertz values for sound in class by just ringing tuning forks, okay? So for sound, though, we could say when it comes to frequency, it represents the pitch of sound. So that's what frequency is for it. Okay. So 256 cycles per second is a middle C note, and it has that pitch. So people who have perfect pitch are able to distinguish variations in different frequency sounds. So this middle C note is 256 cycles per second, or 1/2 or 256 hertz. So that sound has a specific pitch to it that we can notice. Any instrument or voice that creates that note is vibrating at that rate of 256 cycles per second. Low rumbly sounds correspond to low rates of vibration, and high squealing sounds are caused by high rates of vibration. And we'll go through various hertz pitches using a frequency generator on the computer, and we'll do that in class. Okay, and then with light, we have the frequency represents different flavors, so to speak, of light. For example, just in for the visible range, different frequencies are represented by different colors. Light itself is on, you've all heard of the electromagnetic spectrum, I'm sure, is a range of different frequencies and different wavelengths, but all traveling at the same speed and includes things like radio waves, microwaves, the infrared, the visible, the ultraviolet range, X-rays, and gamma rays. And so we have things like the radio waves, which we know are picked up by, our radios. And those have large wavelengths, okay, and frequencies that are smaller. And then we have really short wavelengths for things like X-rays and gamma rays that have a very high frequency. And the higher the frequency, actually, the higher energy of the wave. So that can cause more damage as well. So you're given the electromagnetic spectrum in your reference table, and it goes through it all. You can see that the visible range here is only through a small region of the actual spectrum at around 10 to the minus 6 to 10 to the minus 7 wavelengths, a frequency of around 10 to the 14, 10 to the 15 hertz. So that's a lot of vibrations per second so light has a very high frequency, much higher frequency than sound. It also travels much, much faster than sound does. And so there's some differences between sound and light, some huge differences, really. But the main thing being, or one of the main things being, that they travel both as waves. So frequency of light is perceived by us in a few ways. There's a small range of light that we sense as color, the visible range. Red light has a frequency of 4 times 10 to the 14 cycles per second. Or hertz, which we abbreviate HZ. Light can vibrate very fast. Visible light is not the only flavor of light out there. We have heat and X-rays, microwaves, radio, and we have our reference table to look at that. Okay, so the next wave property we're going to look at is the wavelength. And we alluded to what that was a moment ago, to where we have a wave, let's say, that looks like this. And the wavelength, one way to easily define it, is between crest to crest, but it's any point on a wave to that equivalent point elsewhere on the wave. And the distance that wave travels before it repeats itself, we could say. Called the wavelength. And this wavelength symbol looks like that, which is lambda. Okay. Greek symbol lambda, and that represents the wavelength. And it's measured in a typical length, which would be like meters or something like that. So the wavelength would be like 0.2 meters, because it's the length, of course. The wavelength can be measured conveniently between crest to crest or trough to trough for in-phase structures. Waves are in phase if they vibrate at the same time. So here would be another wave that's in phase with the wave that I already drew. Sort of. Draw it very well. Okay, so that's wavelength. The next thing we'll look at here, the next property, is called the amplitude. And the amplitude shows how much energy is being transferred. Okay, remember, waves transfer energy. And the amplitude is sort of a representation of how much that energy that wave is traveling. Let's say we whistle a middle A. Middle A has a higher frequency than the middle C. The middle C was 256, but the middle A is 440 hertz, or cycles per second. Okay? So let's say as a representation of that, we drew a wave of that middle C that looked like this. And the high points and the low points are where we have compressions and what are called the separated areas of air molecules, which are called rarefactions. So we have compressions and rarefactions of air molecules going forth from the whistling A. If you whistled into a megaphone, it would look different, somewhat, okay? Because the megaphone would make it louder. But what's the same? Well, the same is that it's in phase. It has the same wavelength, but now it has a different amplitude. So that has a small amplitude. The louder one has a larger amplitude. So the energy of the wave is stored in the amplitude of the disturbance. We could think about water waves. Taller waves do more damage. The energy is proportional to the square, actually, of the amplitude. So energy, we say, of the wave is proportional to A squared. So if you double the amplitude, you're actually 4 timesing the energy of the wave. And that goes all the way back to the same sort of principle of, of relating to a 3-dimensional sphere that's being generated, because we've been drawing waves in 2 dimensions, but it's actually in 3. So half the time the amplitude of the wave is negative, but the energy is still positive. So in sound waves, the amplitude indicates the volume. And in light waves, you could probably guess this. The amplitude is brightness. Okay? So we had frequency before, which for sound represented the pitch of the note, and for light represented the flavor, and for visible light it's the color of light. And amplitude for sound is volume, and for light it's brightness. Okay? So the energy of the wave is the loss in the amplitude as the wave propagates. If someone yells in your ear, it hurts, but if someone yells on the other side of the gym, it sounds much softer. Why is that? Well, we've been drawing waves in 2 dimensions, but really it's 3 dimensions coming out from a person. Okay? So if we have a person here yelling out, the wave is actually going to travel out from that point in three dimensions around it, so it's a sphere. And these sound waves will go out in all directions. The energy in the wave comes from the work you did shaking the muscles in your throat. So the initial spherical waves you make have a small amount of surface area that it's distributed on, just like the model for the brightness of the light, or the model for the gravitational amounts that we came up with earlier. As the sound moves away from you, the energy is the same, but the spherical waves get bigger, so the surface area gets bigger. So the density of the energy, the amount per any sort of point on that sphere, goes down by, in a relationship to 1 over r squared from the source that you're at. Okay? So energy density goes down by this amount. It's spreading out on the sphere around there. So if someone yells in your ear, it's very loud. You're very close to the sound source. But if someone's yelling in a gym, all that sound has to spread out in three dimensions. And you have to share that same amount of energy with everybody else that's on that sphere with you, with all the sound spread around there. Now, this is why lasers actually don't seem to lose their brightness. Shine a laser across to a point like across the street, you can still see it is quite bright. And what it does is it concentrates the light in one dimension, so it doesn't actually spread out from the source. It keeps it focused in one dimension, so when it gets to the point and hits something, then you can see it light that area up. Okay, so that's energy and amplitude. The next part we'll talk about is speed and the medium that it's traveling through. Okay, so we've been talking about the propagation or motion of waves. There are two important aspects to the motion of the waves. First of all, we need a way to calculate the speed of waves as they travel. Okay, so if it was just a wave pulse, so instead of just a continuous wave that I've been drawing like this, but just a wave pulse, a wave pulse would look, something like that, and it would travel forth, like in that direction. So that is some time later, as it's traveling through this medium, it's moved in some amount of time, it's moved a distance, delta S, right, from here to here. And that's occurred over some time period. And we, of course, know that the average speed in there would be delta S over delta T. So that would be the speed of the wave, distance over time. For continuous waves like this, we can write this equation. V equals lambda times F, the wave equation, sometimes called. Well, it's nice for a lot of reasons. One is it's simple, but here we have speed. This one we have wavelength. And here we have frequency. And so that says that the speed of the wave is the wavelength, the distance between equal points on a wave, times how many times it goes each second. That seems to make sense, doesn't it? Because we know the units for, speed are meters per second. The units for wavelength are meters. And the units for frequency is 1 over second, so we could see that that works out. So if you want to get the speed of a continuous wave, just take its wavelength and multiply by its frequency. Okay? It tells us that waves of a specific type travel at the same speed. Different frequencies of waves just have a different physical size to them, okay? Larger size. So light and sound travel at very different speeds as well. In air, speed of sound is 330 meters per second at temperature of around room temperature. In air, the speed of light is 300 million meters per second, much higher than the speed of sound. Okay? So here's an example. Okay, what is the wavelength of that middle C that we played at 256 hertz? Well, it's going through sound, through air, and it's sound, and it's equal to lambda f. So we know what V is. It's 330 meters per second equals lambda times the frequency of 256 1 over seconds. So lambda would be 330 divided by 256. 1.29 meters. That might be higher than you expected, but it is the case of these, and that's the distance between like successive compressions of air as it vibrates. 1.29 meters. Okay, here's another example. Okay, what is the wavelength used by an FM radio station transmitting at 103 megahertz? Okay, well, if you look up mega in your reference table, you can see it's million, 10 to the 6. So the frequency here is 103 times 10 to the 6 hertz, or 1 over seconds. Now, radio waves are a form of light. So they travel at a speed of 300 million, or an easier way to write that is 3 times 10 to the 8 meters per second. So you could see that you have to get used to scientific notation here. Okay, and you have to be careful, we've done this before, with dividing by scientific notation and things like that, because you want to make sure that you're treating it as one number, right? So you can use your E button on your calculator to do that. So the wave equation is V equals lambda F. So once again, lambda is V over F. But in this time, it's the speed of light, which is 3 times 10 to the 8 meters per second, and the frequency, which is 103 times 10 to the 6, 1 over seconds. So in my calculator, I'm going to say 3 double E gives me 1e to the 8, divided by 103 double E gives me 1e to the 6, gives me 2.91 meters. Great. Now, speeds of light and sound, specifically in air, the material that a wave is traveling through is called the medium. Okay, so these waves are going through different mediums. So sound may travel through air, and it may also travel through train tracks. You could go or other solids, put your ear on the train tracks, and you can hear the train coming from a ways off. It travels through water. Think of when you're under the pool and you're yelling to a friend under the water. It's muffled. But the sound is still traveling through it. Okay. Light travels through glass, travels through air. It also travels through space. So how does sound get from one place to another? Well, it uses atoms and molecules as its medium. We'll do a little activity to demonstrate that. But as the vocal cords shake and bump into the molecules of air, it creates compressions and rarefactions that move out from each other based on how much it's vibrating back and forth. So the bumped molecules then hit other adjacent molecules, and so that bump starts traveling out. So it travels like bumping into one, bumping into the other, and it works like a domino effect. Okay, one domino hits the next domino. If the sound travels like treating atoms like dominoes, we're not saying the sound is wind. We're not moving wind. It's just vibrating molecule to molecule. Okay. The speed of sound is different in these different densities, right? Because if the molecules are closer together, like in water, then the sound's going to travel faster because it's easier to knock in from one to the next because they're closer. So the speed of sound in water is actually 1,200 meters per second compared to only 330 meters per second in air. In a solid, the speed of sound can be as high as 12,000 meters per second. Now, we need these dominoes, we need these molecules for sound to travel. So sound does not travel in a vacuum. We'll do a little demo with that, with ringing a bell in a vacuum that we create by sucking all the air out. We won't be able to hear the bell much because there's no air for the sound to travel through. So in space, when you see things like in WALL-E, where Eve is calling, WALL-E, in fact, unless they're communicating through light waves and speakers, you wouldn't actually hear a voice across there because the sound would not travel through space. But light works differently. It does not travel by shaking atoms, okay? So light gets here from the sun, doesn't it? And there's no air molecules in space. There's no molecules, so for most of its journey, it's traveling through the vacuum. And in fact, it likes that because light actually creates its own medium. We'll talk about that more later. And when it gets to stuff like air or water or glass, light actually slows down because it has to act to vibrate electrons on atoms, and that vibration slows the light down. We'll talk more about the speed of light and how that varies and what sort of cool things that actually creates later in the unit.